In this episode, we're looking at the complex relationship between soil mechanics and hydrology, specifically how shallow foundations behave when the groundwater level rises above the footing base. Designing for a Phi-C soil, which possesses both internal friction and cohesion, requires a nuanced approach to bearing capacity. When your water table sits between the ground surface and the embedment depth, D_F, you aren't just dealing with soil, you're dealing with a submerged environment that fundamentally alters the effective stress of the system. For an infinitely long strip footing, the primary concern is the reduction of the soil's unit weight. As water fills the voids, buoyancy forces kick in, effectively cutting the soil's contribution to stability in half. In the standard Terzaghi or Meyerhof bearing capacity equations, the second term, representing the surcharge, must be adjusted. You'll need to calculate a weighted average unit weight, gamma_AVG, for the soil above the base of the footing to account for the dry crust near the surface and the submerged layer immediately below it. Moving to square footings, the geometry adds a three-dimensional constraint to the failure slip surface. While the fundamental physics of the water table remains the same, shape factors, S_C and S_gamma, must be applied to the cohesion and self-weight terms. The presence of water in the embedment zone means the effective overburden pressure, Q, is significantly diminished. If the water table is at the surface, Q is calculated using the submerged unit weight, gamma prime equals gamma sat minus gamma W, which can lead to a drastic reduction in the allowable bearing pressure compared to a dry site. The C, or cohesive component of the soil, provides a critical safety net in these scenarios. Cohesion is generally considered independent of the effective stress, meaning the first term of the bearing capacity equation, C'(n)C, remains relatively stable regardless of the water level. However, if the soil is prone to softening or saturation-induced strength loss, that cohesion value might need to be downgraded. It is vital to perform drained or undrained analysis depending on the loading rate and the drainage characteristics of the specific silt or clay sand mixture you are encountering. The Phi, or frictional component, is where the water table does the most damage. Because the frictional resistance of soil is directly proportional to the effective normal stress, the third term of the bearing capacity equation, the 0.5 gamma B n sub gamma term for strip footings, or 0.4 gamma B n sub gamma for square footings, must use the fully submerged unit weight. This is because the failure zone extends beneath the footing into the saturated zone. Ignoring this can lead to an overestimation of the soil's resistance and potential shear failure. Ultimately, designing for this in-between water state requires a conservative eye on the unit weights used in each part of the calculation. Whether you are modeling a long retaining wall foundation or a square column pad, the transition from bulk unit weight to submerged unit weight is not a toggle switch, but a gradient based on the exact depth of the water. Accurate field measurements of the seasonal high water table are essential, as a foundation that is safe in the summer might face a critical reduction in capacity during a wet spring.